Hi guys, we'll now dig in to the concept of the numerical differentiation. Okay? So, nung math series nyo, nag-differentiate tayo analytically, di ba? Madali lang kumuha ng mga derivatives ng mga polynomial functions, trigonometric functions, and kahit anong functions. Memorize naman natin yun by heart. Pero there is another way of finding the derivative of a function at a certain point numerically. Okay? So, yun yung i-discuss natin this time. Okay? So, for this content, we'll explain yung in-depth concept ng differences na na-mention din sa mga modules natin sa ODEs and PDEs. Okay, so with this content, magigets natin kung ano ibig sabihin ng mga differences na ito. Okay, okay, ano nga ba yung numerical differentiation? This is the computation of values of the derivative of a function from given values of f. Ibig sabihin, makapag-numerical differentiation ka lang kapag may given values ka ng f. Okay, so ibig sabihin kahit hindi mo alam yung uh, function, as long as may data ka ng values ng f, okay lang. Okay? Pero as much as possible, ina-avoid yung numerical differentiation. Kasi as long as much as possible, ina-avoid siya, lalo na kung kaya mo nang kunin yung derivative analytically. Pero bakit pa rin tayo gumagawa ng or nagsisolve ng derivatives numerically? Isa is we might know the value of the derivative at as a sample dataset. Sabi ko kanina, ginagamit lang naman to kapag may dataset ka tapos hindi mo alam yung function. Pwedeng interested tayo sa kung ano yung changes dun sa dataset natin. Next would be yung exact computation ng derivative. Masyadong mahirap. Okay, sobrang pangit na ng function natin na in such a way na sobrang daming evaluation ng derivatives na mangyayari. Okay, so maging useful yung numerical differentiation. However, sabi ko nga, avoided siya as much as possible. So, sige. Yung simple approximation ng first derivative, paano siya kinukuha? Ito. Parang galing sa limit definition. So, if you have a function, and then a line, okay, ano ba yung definition ng derivative? Diba? It's the slope of the point, of the line at a certain point sa function. Okay? So, sa case na to, ina-approximate natin yung derivative using a secant. Okay? So, kinukuha natin yung change in y. So, yung function value natin sa point na to minus yung function value sa point na to para makuha yung height na to. Then, divided by the h or yung layo ng dalawang points na pinagkukunan natin. Okay, with that, makuha natin yung slope ng secant. However, kapag sobrang layo ng dalawang points na to, sobrang layo niya dun sa derivative, di ba? Kasi ang slope nandito eh. Malayo pa siya. So, paano natin mapapalapit yung secant sa tangent? Papalitin natin, papalitin itong h na to. Pero dapat yung h na yun is greater than 0 pa rin. Okay? So, yun yung ginagawa dito sa numerical differentiation ng first derivative. So, approximation using this formula. Okay? So, galing na siya sa limit definition ng derivative. So, as long as yung h papalapit na papalapit sa 0, liliit na liliit yung h na yon, yung distance na to, halos magdidikit na yung dalawang points na yan, di ba? Parang ganyan na. Isa na lang. Halos magiging tangent line na siya. Kaya siya yung limit definition ng function ng first derivative. Okay? So, kapag nag-approximate tayo, yung h dapat natin small. Okay? However, for almost all functions, the equation given does not give the exact derivative. So, lahat ng functions, almost lahat ng function, itong equation na to, hindi niya mabibigay yung exact derivative. Pakita natin. For example, we're asked to approximate yung derivative ng function na to at x equals 1. Okay, using different h values. So, ito nag-try siya ng h values from 1 until 1 times 10 raised to negative 17. Okay, ano yung formula natin? Diba? F of x plus h minus f of x over h. So, solve natin yung f of x plus h. Ibig sabihin, f of 1.1. Kasi ang x natin is 1 eh. So, 1 plus 1 is 2. So, f of 2, substitute mo yung 2 dito sa e raised to x. That's equal to this, 7.39, 7.389050, Okay, so that's e raised to 2. Ano yung f of x? F of 1, which is 2.7182818828. Okay, and then difference nila, ito yung numerator ng formula natin, di ba? Ito. Subtract ko sila. Ito yung difference. And then divide by h, which is 1. So ito yung approximate value ng derivative natin. First derivative. Okay, let's move to the next h, yung 0.1. If your h is 0.1, yung f of x plus h is f of 1.1. So e raised to 1.1. Okay, you should get 3.0041666024. Okay, lahat ng to pare-parehas lang kasi f of 1 lang naman yan. Ibig sabihin e raised to 1. So value ng e lang yan. Okay, and then this one is the difference between the f of x plus h and the f of x. So subtract ko to. Subtract ko ito from here. You get these values. And then divide ko by h to get this first derivative approximation. Okay, and then you get the following. And as you can see, sa gitna, pagdating ng 0.00000001 tsaka 0.0000000001, halos dumidikit na, di ba? Yeah, actually, ito madikit na yung totoong, di ba, ano ba yung derivative ng e raised to x? Di ba, e raised to x pa rin. So, pagdating sa h na to, papalapit na siya ng papalapit dun sa value nung first derivative talaga. However, paglampas niya, parang lumalayo na naman ulit siya hanggang sa maging 0, di ba? Yung approximation natin, sa sobrang liit, pag super small na yung h natin, yung approximation natin 0, di ba? Kaya nga sinabi dun sa previous slide na for almost all functions, yung equation na yun, hindi siya magbibigay ng exact derivative. Okay? Kasi, yeah, may part na papalapit siya ng papalapit, pero sa certain part, papalayo na rin siya ng papalayo. Sorry. So, from here, pag ganyan, papalayo dun sa totoong value ng first derivative. Okay? So, ano ba yung problem dito sa h na to? Una, kapag sobrang laki nitong h, parang sobrang ano na rin, yung secant line, wala lang yung ano kanina. Di ba? Kung sobrang laki ng h, sobrang layo. Secant na talaga yung kinukuhaan natin ng slope. Okay, hindi na sobrang lapit yung dalawang points. However, pag sobrang liit naman ng h natin, sobrang magkadikit na nung x, di ba? Nung x plus h, saka nung x. So, magdidikit na yung function values na to, halos magiging 0 na, di ba? Yung difference nila. So, kaya nga dito sa super small na h na to, halos 0 na yung value nung first derivative. Kasi nga yung numerator, sobrang dikit na niya sa isa't isa. Yung x plus h saka yung x. Okay? Halos wala ng difference. So, saan ba nanggagaling yung approximation errors na yun? Recap lang natin yung Taylor series approximation kung natatandaan nyo pa. Ginagawa natin for numerical differentiation ay nag-approximate tayo ng function as a polynomial. Okay? Ginagawa, di ba yung Taylor series natin, Infinite yan. Ginagawa natin finite. Nagtatangkate tayo. Okay, so consider natin yung Taylor series expansion na may first n terms lang. So, ito yun. F of x plus h. So, yung f of x plus h, that's equal to f of x plus h times first derivative plus h squared over 2 factorial times second derivative, and so on and so forth. Ito yung pang n na term. Okay, that's h raised to n minus 1 over n minus 1 factorial times the n minus 1th derivative of f of x. Okay, di ba infinite yan? So, saan napunta yung succeeding terms? Siya na ngayon yung tinatawag na error dahil dun sa truncation. Okay, na-account siya by lumping yung subsequent derivatives into one term. So, lahat ng susunod pang derivatives from from the nth derivative until the infinite derivative, pagkasamahin niya lang into one term. So, h of n, h raised to n over n factorial times the nth derivative of f at a value psi, which is between x and x plus h. Okay, so yun yung definition ng error term natin sa pag-truncate ng Taylor series expansion. Sobrang nakakasakit sa ulo, pero simplihan natin, gawin natin, first two terms lang. Okay, ibig sabihin hanggang first derivative lang yung i-consider natin. Looking at this next slide. Yun nga, sabi nga, since yung result natin nag-truncate tayo, nagputol tayo, may approximation error na mangyayari. And assuming na at least 2 lang yung derivatives natin, okay, hanggang second derivative lang. So yung f of x plus h natin equals f of x plus h times f prime of x. Okay? Yung lahat ng succeeding na derivatives, ito na siya. Nilamp lang natin dito sa error term na to, which is h squared over 2 times the second derivative of f at a certain value, psi. Okay? And then, since gusto nga natin makuha yung first derivative, i-rearrange lang natin ito. Lipat natin ito dito. Okay? And actually, ito rin. And then divide both sides by h para matira si f prime of x. So if you rearrange this equation that way, makuha mo f prime of x equals f of x plus h minus f of x over h. Ito yung ginagamit natin approximation kanina. Okay? So ibig sabihin, para maging exact yung answer natin, kailangan pa natin ito i-add, i-subtract. Si h minus 2 over, h over 2 times the second derivative of x at the value psi. However, hindi natin sinusolve. So, approximation lang talaga yung kinukuha natin. Ito yung error term dahil dun sa approximation. Sorry. Yan yung error. Sorry. So, ito yung approximation natin using a numerical method. So, ito yung approximation error or yung truncation error dahil dun sa ginawa natin sa pag-truncate nung Taylor series natin. Okay? Sige, ito for ano lang to ha, for the first derivative lang. Okay. Yung error, may order of error din yung mga natin, yung method natin. Okay, may accuracy rin siya, yung order of accuracy. Makita natin siya dun sa power or exponent ng h dun sa truncation error. So kung babalikan natin yung first derivative na approximation natin, h lang to, diba? H over 2. Ibig sabihin, since 1 yung exponent ni h, first order method itong formula na to. Okay? And ano yung tawag sa formula na to? This is actually called a forward difference quotient. Okay, diyan na papasok yung mga differences na encounter natin sa mga ODEs and PDEs. Again, this has an order O of H and thus a first order method. Okay, again, nakadepende ang accuracy ng method natin sa power or sa exponent ni H. Sabi ko nga, it's a forward difference quotient kasi uh, kukuha tayo ng values based on, uh, nagkukuha tayo ng derivative based sa values ng function sa x, tsaka sa x plus h. Okay, ibig sabihin sa current value, tsaka sa next iteration. Okay. So, ito yung approximation formula na yun, f of x plus h minus f of x over h. Yung isa naman is yung backward difference quotient. So, instead na current tsaka yung next iteration, ngayon naman is yung current tsaka yung previous iteration. Okay, so ang formula dito is f of x minus f of x minus h over h. Okay, nakuha lang din to galing sa Taylor series truncation. Okay? Ito yung best na x plus h, x minus h yung sinubstitute. And if you combine yung forward difference and yung backward difference na formula together with the error terms, makukuha mo yung central difference quotient. Okay, so pinagsama niya itong dalawa. Ito yung forward, ito yung backward. So you can see 2h na yung denominator kasi ito yung dalawang points na hinahanap natin or kino-compare natin. Pinagkukuha natin ng derivative. So 2h yung distance between the 2 points. Kaya yung difference. Ayun yung denominator. Okay, and then yung difference ng function values at x plus h and x minus h. Yun yung numerator natin. Okay, kung titignan yung magiging derivation niyan sa Taylor series din, sabi ko nga, that's the combination of the backward difference and forward difference. Makikita nyo na higher accuracy siya kasi yung error term natin or yung truncation error natin, h squared yung order. So this is order O of h squared. Okay, using Taylor series lang yan na hindi na natin papakita. Gusto nyo makita yung derivation, you can read on that supplemental readings sa free time ninyo. But ang kailangan lang naman natin dito kapag nag-solve na tayo is this approximation formula. Okay, hindi naman natin sinasolve itong value na to and itong buong to kasi hindi naman natin kailangan yung exact kasi nga nag-approximate lang tayo. So ito yung gagamitin natin. And yung higher order pa is O of h raised to 4. Ibig sabihin yung fourth order na yan, ibig sabihin yung exponent ng error term natin ay 4. Okay? H raised to 4. Ito naman yung formula ng approximation for that order. So, pag higher order, mas accurate yung value. And yung mga higher order na yan, nanggaling lang din yan sa forward and backward differences. Okay, combination na. Let's present an example para lang mas maging clear. Let's say, meron tayong function which is equal to cosine of x. We're asked to calculate the approximation for the f prime of point 8. Ibig sabihin, first derivative of our function at x equals 0.8. Pinapagamit sa atin yung central difference approximations with step sizes 0.1, 0.01, 0.001, 0.00001. Tapos compare daw sa true value ng first derivative ng function natin at x equals 0.8. Ano ba yung derivative ng cosine? Di ba negative sign of x? So, negative sign ng 0.8. Compare natin lahat ng approximations na makuha natin at different step sizes na h. And then, compare natin yung difference nila from the exact or true derivative. Pinapakuha sa atin is 9 decimal places. Madali lang ito gawin kapag naka-Excel. Okay? So, ito yung dalawang formula na yun. Yung sinasabing central difference approximations. Ito yung second order. Ito yung fourth order. Again, hindi natin kailangan isolve itong term na to ha. Kasi sila yung mga error term. Ibig sabihin, nanggaling sa truncation error. Since approximation lang tayo, yung approximate formula lang yung gagamitin natin. Okay, so let's start with listing down the different step sizes 0.1, 0.01, 0.001, and 0.0001. Unahin natin yung second order approximation. Okay? So basically, kapag h equals 0.1, ang gagawin mo is isosolve mo si f of x plus h. Ano ba yung x natin? 0.8, di ba? So, 0.8 plus 0.1, that is, so sulat ko na lang din, 0.8 plus 0.1 minus f of 0.8 minus 0.1 divided by 2h, or 2 times 0.1. Okay, so that's equal to f of 0.9, ibig sabihin substitute natin si 0.9 dito kay cosine x. So cosine ng 0.9 minus cosine ng 0.7 over 0.2. Okay? Sige, try nyo sa calculator nyo. Dapat naka-regions ha, kasi ang Excel natin naka-regions, default yung mga angles. And pati na rin sa coding, sa program, sa code natin, naka-regions yan. So you should get negative 0.716161095, as you can see here. Okay? Ganun lang din yung gagawin nyo for h equals 0.01. Try nyo lang, substitute yung 01 dito. 0.0001 and 0.0001. Okay? You should get these values. And then we are asked to compare daw sa true value ng first derivative, di ba? Ano ba yung first derivative? Negative sign ng 0.8. And if you solve that using your calculator or using Excel, sign ng 0.8, that's equal to negative 0.71735, okay, negative 0.717356091. Okay? Kunin mo yung absolute difference itong dalawa. Ibig sabihin, subtract mo and then get the absolute value. Okay, you should get this one. Okay, 1194996. Okay? And when you subtract this and this, kinuha yung difference, absolute difference nila, you get this and this and this. And as you can see, pagdating ng 0.0001, ano naman, malapit naman na siya. It's close enough sa true value ng first derivative ng function at x equals 0.8. Okay. Similar lang sa fourth order approximation, instead na ito yung formula na gamitin, ito lang. Okay. So at x at step size na 0.1, ang mangyayari, negative f of, okay, 0.8 plus 2 times 0.1. So 0.8 plus 0.2, f ng 1. Value ng function natin at x equals 1 plus 8 times value ng function natin at 1 point, di ba, x plus h, so 0.8 plus 0.1, 0.9. Ayan na to. So function value natin at 0.9. Okay, and then minus 8. Sorry, mali pala yung binox ko kanina. Kulang. Okay, so minus 8 times function value natin at x equals 0.7. Finally, plus function value natin at x equals ilan? Minus 0.2. Okay, so 0.8 minus 0.2, 0.6. And that's divided to be divided by 12 times 0.1. So that's 1.2. Okay, and if you solve that, you should get negative 0.717353703. Okay? So, parang negative ng cosine ng 1, negative cosine ng 1, plus 8 times cosine ng 0.9, minus 8 times cosine ng 0.7, plus cosine na 0.6 divided by 1.2. Okay, tama naman. I got negative 0.717353703. Okay, and then you get the absolute difference of that dun sa value ng negative sign 0.8. You should get this absolute difference. And as you can see, pagdating agad ng 0.01, sobrang lapit na agad, di ba? Halos 0 na agad at this 9 decimal places. Sobrang lapit na agad. So, dahil fourth order approximation yung ginamit natin. Okay? So, as long as mataas na yung order of approximation ng formula natin, kahit maliit pa lang yung, kahit hindi pa ganun kaliit yung h, kaya na agad i-approach ng malapit sa true value. Right? We also have another numerical differentiation using interpolation naman. Okay, ito naman yung magagamit lang or useful lang kapag may dataset ka. Okay? May data values ka lang x and y. Okay? Hindi natin ito masyadong i-discuss deeper kasi hindi naman natin siya kailangan further sa course na to. Pero let's just introduce this. So may set ka ng ordered pairs x and y. Okay? Tapos from there, makukuha natin yung approximation ng derivative. Paano? By direct differentiation ng interpolating polynomial. So given sa atin yung interpolating polynomial. Usually, Lagrange polynomial yung binibigay. Okay, and then the derivative at any point is determined by the algorithm na to. Hindi ko na siya masyadong i-discuss, but basically this is your derivative approximation and this is your truncation error. So basically, ang nangyari lang is you're multiplying your function value and the derivative of your interpolating polynomial. Siya yung L. Okay. Kunin mo yung derivative ng interpolating polynomial mo and then multiply that to your function value. Okay, sige. Mas madali ito kapag tinignan natin yung example. So, sa example na to, ang gagamitin lang is linear Lagrange interpolation. So, linear Lagrange yung interpolating polynomial natin. Ito yun. Okay, so P sub 1 of x is equal to L sub 0 of x times f of 0 plus L sub 1 of x times f of 1. Okay, so ano yung L sub 0? Ito yun. And then L sub 1 of x. Yan yung mga interpolating polynomial, di ba? Sabi ko yung Lagrange polynomial, L. So, kunin mo yung derivatives nitong dalawa. So, ano ba yung derivatives niyan? Ang ano lang naman dyan, ang variable lang naman dyan is yung x eh. Lahat nitong natitira dito are constants. So, ang derivative ng x minus constant is 1, di ba? Derivative ng x is 1. Derivative ng constant is 0. So, 1 lang matitira sa numerator. Yung denominator natin, ma-retain lang kasi constant yan na parang nakamultiply dun sa x natin. So, ang first derivative ng Lagrange polynomial natin is 1 over x sub 0 minus x sub 1. Okay, for L sub 1 naman, ganoon din, 1 over retain lang yung denominator. Okay, balikan natin yung formula. Saan na yan? Yan. So, we're gonna multiply yung derivative ng Lagrange polynomial natin sa function value. Okay, and then get the summation. So, yun lang talaga yung gagawin natin for this example. Nakuha na natin yung derivatives ng Lagrange polynomials, yung L sub 0 prime and L sub 1 prime. Okay? So, for this case, kunin din natin yung derivative nito. Kasi ito yung kukuha natin ng derivative eh. Okay, so P sub 1 prime of x is L sub 0 prime of x times f sub 0, L sub 1 prime of x times f sub 1 plus yung error term. Okay? So, substitute lang natin nakuha natin derivatives kanina nito. Ito, substituted here. This one substituted here. Okay, and then yung error term natin, or yung truncation error. Right? Sige, gamitin natin yan. Ay, sorry. So, yan yung parang linear Lagrange interpolation. Okay, ang given sa atin na points are x sub 0, f of 0. So, ordered pairs yan, x sub 0, f of 0, f sub 0, and x sub 1, f sub 1. Okay, substitute lang yan. Makuha mo na yung approximation for your derivative, first derivative. Okay? Pero hindi naman natin yung gagamitin for this course kasi more on the difference methods tayo. Okay? So, paano, sir, paano pag higher order derivatives? Okay, iba yung order kanina ng approximation sa ano ha? Sa order ng derivatives. Yung order ng approximation is kung gaano ka, tawag dito, gaano ka accurate yung approximation natin. Pag order naman ng derivatives, kung pang ilang derivative, first, second, third, so on and so forth. So, yung pinakita natin kanina is first derivative lang. Pero pwede naman natin i-extend, di ba? Yung Taylor series, infinite naman yan. So, pwede natin i-extend yung Taylor series such that maabot hanggang yung higher derivatives natin. Okay? So, meron tayong higher. Ang typical order nung approximation is second and fourth pa rin. Diba? As we have shown kanina sa first derivative, medyo kahit maliit na yung, kahit hindi ganun kaliit yung h, medyo malapit na siya sa exact value. Okay? So, higher order derivatives natin, ito yung formula for second order. Okay. So, first derivative, ito yung ginamit natin kanina. As you can see, this is central difference. Okay. Ito naman yung sa second derivative, third derivative, and fourth derivative. Okay, central difference lahat yan. Okay, yan yung formulas for approximation. Okay. Ito naman fourth order approximations. Ibig sabihin yung error term nito may h raised to 4. Okay, pero hindi na natin pinakita dito. Okay, so ito yung mga formula and wag lang malito dun sa mga terms na yan. Ito naman ibig sabihin kapag yung subscript is negative 3, meaning lang yan f of x minus 3h. Pag f of 2, ang ibig sabihin lang yan ay f sub 2, ang ibig sabihin lang yan is f of x plus h plus 2. Okay, so basically ang numerical differentiation madali lang siya kasi more on substitution lang. And hindi mo kailangan kabisiduhin yung formula kasi provided naman na yan. Alright? So, don't be afraid dito sa problems involving numerical differentiation. So, isang example, last na. We're given f of x equals cosine x pa rin. Pinapaharap naman sa atin yung higher order derivative. Okay, ito second order approximation ng second order derivative, no? Kung natatandaan nyo sa list of formulas kanina. Okay, pinapakuha yung second derivative ng x of 0 ay ng function natin at x equals x of 0. Okay, pero for this case, ang pinapahanap sa atin is approximation ng second derivative ng function at x equals 0.8. Tapos ito yung step sizes na pinapatry sa atin, 0.1, 0.01, and 0.001. And then pinapakompare yung makuha nating approximation with the true value ng second derivative. Okay, tama naman, negative cosine kasi ang first derivative ng function ng cosine natin is negative sign, di ba? Negative sign of x. And then, second derivative would be negative ng cosine of x. Okay, so yan yung pinapa-compare sa atin. Negative cosine ng 0.8 kasi yan yung true value. Okay, let's look at the tables. So, tatlo lang naman yung pinapahanapan sa atin ng approximation. Tatlong step size lang. So, ito lang. Simple lang naman ito. So, yeah. F, second derivative ni f at 0.8, yung approximation natin dyan would be f ng x plus h. So, 0.8 plus 1, 0.9 plus, minus 2 times the function value at x. So, f of 0.8. And then, plus f of x minus h. So, 0.7 yan. Over h squared. So, 0.1 squared. Okay. Substitute natin yung mga function. Makuha mo dapat cosine ng 0.9. Again, dapat naka-regions yung calculators. No? Minus 2 times cosine ng 0.8. And finally, plus cosine ng 0.7. Forgive my handwriting. Over 0.001. Okay, you should get what value if you try solving sa calculator nyo. Cosine ng 0.9 plus cosine, minus 2 times cosine ng 0.8 plus cosine ng 0.7 divided by 0.1 squared or 0.00. Should get negative 0.6969126313 pag 9 decimal places. Okay, ganun lang din gagawin kapag 0.01, substitute mo lang 0.01 sa h and then x is 0.8. You should get the following. Okay, and then yung error natin, absolute error, gawin mo lang, subtract lang natin tong values na to from negative cosine ng 0.8 which is equal to na negative ng cosine 0.8 is negative 0.69 67067. Okay, subtract mo yan. I get the absolute value, you get the following absolute errors. Okay. Alright. So, yun na. As you can see, second order ito ng second order approximation for the second derivative ng function. So, as we have expected, kahit hindi ganun kaliit yung h natin, yung step size natin, medyo malapit naman na dun sa true value ng second derivative. Okay? You should just try this at on your own kung makuha niyo yung mga values na to using the steps na pinakita ko. Okay? Okay, that ends our discussion on numerical differentiation. If you have questions, again, you can just arrange a synchronous Zoom consultation session with me. Contact nyo lang me via email. Pwede rin magsama ng classmates. Or you can just ask directly sa community forum or course discussion forums natin sa OVLE. Here are our references for the mathematical modules. And that's all. Thank you for listening. That's module 1B. See you next module.